It's a huge pleasure to be here, and I want to thank all of you for coming out tonight. Thank the Sydney Opera House. It's an enormous pleasure to be in this amazing venue, and a great pleasure to me personally to be back in Australia, which I consider my second home, and a huge honor to be on the stage with the legendary David Suzuki and also the heroic Tim Flannery. So I want to talk to you tonight about the end of the world. A very happy subject. And as I was thinking today about tonight's talk, I realized that actually I've been interested in the problem of the end of the world since I was a child. As a child, one of my favorite movies was a film that many of you are familiar with, Nevil Shute's On the Beach. And some of you may have heard the story. You may know On the Beach was filmed here in Sydney, and it tells the story of a group of people who are the last survivors on Earth after nuclear... I'm sorry?
Melbourne.
Oh, Melbourne. I apologize. Well, I was in Melbourne yesterday. I must still be jet-lagged. But it tells the story of a group of Australians who are the last survivors on Earth as the nuclear fallout from World War III makes its way to Australia. And reportedly, Ava Gardner, the star of the film, when she arrived in Melbourne, said, "Oh, this is a good place to make a movie about the end of the world." Of course, Melbourne is a much more sophisticated city today than it was then. But 3 years ago, I had the opportunity to spend a month in Perth. And lo and behold, I found myself writing a book about the end of the world. So I guess Perth is a good place to write a book about the end of the world. The book is called The Collapse of Western Civilization. And you can see the Australian influence here. I spent 3 years in the outback of South Australia, came to love the desert, and you see the desert is the icon here. The book is a message in a bottle. It's a message to our readers. It's a message to everyone to really take seriously, to take to heart the meaning of climate change. When Eric Conway and I were writing the book Merchants of Doubt, we spent 5 years, during which time we read literally thousands and thousands of pages of, frankly, quite depressing scientific studies. Scientific studies that talked about the meters of sea level rise that we would face, and the degrees centigrade of warming, and the parts per million of carbon dioxide and methane that are accumulating in our atmosphere. And after reading through all this work, I began to feel very strongly that this was all obviously tremendously important, but all of this scientists, all this scientific information, all of these numbers didn't really convey to people why climate change matters. What difference does it make if the carbon dioxide in the atmosphere is 350 parts per million, or 400, or 500, or 600? What difference does it make if the average temperature of the globe increases by a degree or 2? Doesn't sound like very much. I mean, if it's 28 or 30, it's still a nice day. So what Eric and I tried to do in this work was to write a story, a narrative, about the human face of global warming, about what climate change means for us as people, and what kinds of dislocations, social, economic, political, and cultural, we can expect to see if we fail to take action to prevent disruptive climate change. So it's really a call to arms. It's not meant to be a prediction. The hope is that we don't follow this pathway because we act on climate change. But in writing this book, it also made me think about another important question, a question that I get asked a lot when I speak in public about climate change. And the question is, how do we know the science is right? So this book is it's a work of fiction, but it's based on facts. It's based on scientific evidence. But as citizens, it's a legitimate question for us to ask, how do we know that that science is right? And if we're being asked to make big changes in the way we live, the way we organize our economy, the way we think, as David is calling on us to do, we have the right to ask the question, well, are we sure that the science is right? And of course, climate skeptics and contrarians and deniers want us to think that perhaps the science isn't right. They want to ask the question, why should we believe the claims of science? So for the rest of the evening, I want to shift gears and actually answer that question. So if anybody asks you, well, why do you believe in the science? You actually have an answer to that question. Now, scientists don't like to talk about belief because for scientists, the word belief conjures up faith and faith seems to be the domain of religion, which, as all of us know, is supposed to be totally different from science. When I think about the question of faith and science and belief and religion, it brings me to the great mathematician Blaise Pascal, who in the 17th century was grappling, he was a scientist, a mathematician, but he was grappling what he thought was the most important question of all facing mankind, which was the existence of God. And Pascal had a thought which came to be known as Pascal's wager. The thought went like this: if I believe in God and she doesn't exist, well, he didn't actually say she, but if he or she doesn't exist, not much harm is done. But if I don't believe in God and God does exist, then I'm going to burn in hell for eternity. And so Pascal concluded that it was rational to believe in God, or as one of my professors in college said, he clutched for the handrail of faith. Now, science isn't supposed to be about faith. It's not supposed to be a leap of faith. But for most of us, it kind of is. Most of us don't really know what the basis is when scientists tell us that the world has warmed a degree and a half, or whatever it is they say. In fact, most of us have very little idea how to judge whether or not scientific claims are true. So we take that leap of faith and we hope for the best. Like Pascal, we assume that the risks of accepting science are smaller than the risks of rejecting it. Now, many of us have been taught that there is a reason to believe in scientific claims, that scientific claims are true because scientists use a particular method that guarantees the truth or the reliability of those claims. And that method, supposedly, is the scientific method. What is the scientific method? Well, many of you were probably taught this in school. It goes something like this. Scientists develop hypotheses, they deduce consequences, that is to say predictions, and they go out into the world to see if those predictions come true. And if they do, we say, yes, the hypothesis is correct. Sometimes, and sometimes scientists do in fact do that, but actually not very often. So here's one example of a case where scientists did do that. When Einstein first developed the theory of special relativity, one of the surprising consequences of that theory was that light doesn't travel in straight lines, but is actually bent in the presence of massive bodies by the bending of space-time. That was a pretty startling prediction, and scientists said, well, if Einstein's right, we should be able to see that effect. And sure enough, in 1918, when there was an eclipse of the sun, Sir Arthur Eddington traveled to Africa, made measurements, and demonstrated that, yes, indeed, lo and behold, the sunlight, the starlight passing near the sun had been bent. And this was considered to be the proof of the correctness of the special theory of relativity. And just 2 weeks ago, just about almost 100 years later, we got the demonstration of general relativity through the detection of gravity waves by the LIGO Observatory that some of you may have read about. Now, sometimes this is called the deductive nomological model because academics like to put fancy names on ordinary ideas. But there is something important about this. It's that in the ideal case, it's not just a hypothesis that we're trying to develop, it's a law of nature. It's what David was talking about, those laws of nature about air and earth that we can't really violate without damaging and hurting ourselves. So in the ideal case, we develop laws, and these laws are invariant. They apply in any place at any time, and it doesn't matter if you're black or white or male or female or Australian or Bangladeshi, these laws will apply. And there are some examples of laws in nature too. E equals mc squared, one of the famous ones. But there are a number of problems with this model of science, and historians and philosophers have done a lot of work to show that the deductive nomological model doesn't really work. It doesn't work logically, and it's not actually what most scientists do. So logically, it doesn't work because of something known as the fallacy of affirming the consequent. And that simply means that a false theory can make a true prediction. The most famous example of this in the history of science is the Ptolemaic model of the universe. As many of you know, Ptolemy and the ancients believed that the Earth was the center of the universe, and that the stars and the planets and the sun all revolved around us. Now, you might think that such an obviously wrong theory would make false predictions. But in fact, the Ptolemaic astronomers were able to make very accurate predictions of the motions of the planets and of eclipses. And so people said, well, obviously this theory is true because its predictions are correct. Today we would say it was false. The second problem with the hypothetico-deductive model is what we know as the problem of auxiliary hypotheses. So when Copernicus came along and said, no, Ptolemy is wrong, the Earth is not the center of the universe, the Earth is in motion around the sun, scientists said, well, if that's true, if that hypothesis is true, then we should be able to detect the effects. And one effect was something known as stellar parallax. So astronomers in the 17th century said, well, if the Earth is moving, we should be able to detect the effect. And one of the effects we should see is that if we look at a distant star, the position of that star in the universe should appear to change as the Earth moves in its orbit. So imagine the Earth is here in December. We look at a bright star like Sirius or Arcturus. Let's see, we're in the southern hemisphere. Can you see? I didn't say Polaris because you wouldn't see that in the southern hemisphere, but look at a bright star. We see it against this backdrop. Now, 6 months later, come June, we look at that same star, and now we see it against a different backdrops of stars. This angle, that angular difference, is the stellar parallax. So this is a prediction. We can see if the prediction comes true. Astronomers did this test, and, whoops, sorry, that went ahead. Nothing. They found no evidence that the Earth was moving. And this is the main reason why most people rejected Copernican astronomy at that time. It wasn't because the idea was crazy or because the Catholic Church wanted to burn Copernicus at the stake. It was because they did the test, and it failed. They were following the scientific method, so something was wrong. Something about this method isn't right, so what wasn't right? Well, we now would say that the auxiliary hypothesis, this extra assumption was being made, and that extra assumption was that the Earth's orbit was large relative to the distance to the sun, so if the Earth moved, we could detect that distance. But today we would say, well, actually, the Earth's orbit around the sun is very, very tiny compared to the distance to stars, and so this parallax is just a tiny, tiny, tiny thing, very, very hard to detect. In fact, it wasn't until the 19th century in the work of Sir William Herschel that telescopes became sensitive enough to detect the stellar parallax. So today we can measure the stellar parallax, but we didn't wait until the 19th century to accept Copernican astronomy. So even if scientists use the hypothetico-deductive model, it doesn't always work. But it turns out that a lot of the time scientists don't even use the hypothetico-deductive model. A lot of science isn't deductive at all, it's actually inductive. By inductive, we mean that scientists go out into the world, they make observations, they see the amazing things in the world around us, and out of all of this observation, scientists begin to understand the way the world works, begin to develop hypotheses and theories to explain the amazing things they're seeing. And of course, one of the most famous scientists in the entire history of science, Charles Darwin, who traveled to Australia and many other places, he didn't use the hypothetico-deductive model. In fact, I often tell my graduate students that actually Darwin is a very reassuring figure, because when he went on the voyage of the Beagle, he had no idea what he was doing. He didn't have a hypothesis to test, he didn't have a theory, he just knew that he wanted to learn about the world and make a difference in the world. So you can start out very confused and still make great contributions to the history of science. In addition to inductive and deductive science, a lot of science involves modeling. And by that we mean that when scientists see things in the world, they sometimes try to explain what they see by developing models of it. In the 19th century, many models were physical models. So this is a picture of a man, a 19th century geologist by the name of Henry Cadell. You can tell he's a geologist because he's wearing Wellington boots and a deerstalker hat. Cadell was interested in a very interesting problem in geology. And that was the question that when you looked at mountains, what you found is that the rocks, the strata in mountains, were very often folded. And sometimes the folds were so big and so large that the rocks were actually folded over on themselves. And so the question was, how did that happen? And how is it possible that rocks, which we think of as being extremely solid, could be folded as if they were a flexible material like rubber or putty? And so he built this physical model with clay and some sand and other materials, and he said, well, look, if we could compress the rocks from the side, it's possible that they might fold and we might form structures like the ones we actually see on Earth. And this became one of the early arguments in favor of what later became the theory of continental drift, that there were horizontal forces pressing rocks, causing them, building mountains, causing them to be folded, and also ultimately leading the continents to move. Now, nowadays, most geologists and earth scientists don't put on Wellington boots and deerstalker hats to do their work. A lot of modeling today is done with computers. They're what we call numerical simulation models, mathematical models. These models play an extremely important role in our understanding of the climate system. And I just want to give you one example of how that works. So many people ask the question, and it's a legitimate one, how do we know that the observed warming of the Earth is caused by greenhouse gases? Fair enough. Well, we can't experiment on the whole Earth. We can't reproduce the Earth in the laboratory, but we can reproduce it mathematically using a numerical simulation model. And when scientists do this, they can take what we know about the thermal effects, the heating and cooling effects of a variety of different factors on Earth. Sulfate aerosols, dust from volcanoes, changes in the ozone hole, changes in the amount of sunlight reaching the Earth, and of course, changes in greenhouse gas concentration. And when you measure the effects of these different factors and put them into a mathematical model, what you see very clearly is that the increase in global temperature, so this is the actual observed temperature, this is the model temperature, and these are these various components that we can put in the model. The only way you can get the model results to match the observations is through this very significant contribution of greenhouse gases. All of these other factors contribute, but they don't explain the warming. Now, this diversity of methods that scientists used led the philosopher of science, Paul Feyerabend, to say that if you ask me what the method of science is, I would have to say, anything goes. Now, this troubled a lot of people because it made it seem as if science was chaotic, and why should we believe science if it's just a chaotic mess of different things? Well, what he was trying to say is the methods of science are diverse because scientists are diverse, and science is a creative process. But if we ask the question, what do all these different activities, inductive, deductive, physical modeling, computer modeling, what do they have in common? They're all means of gathering and evaluating scientific evidence. All science is based on evidence. But then that pushes back the question, and we have to ask, well, who judges the evidence? And the answer, of course, is scientists do. So the question then becomes, what is it really that scientists are doing? And the answer that many people have come to, and that I've written about myself in my earlier work on the history of plate tectonics and continental drift, is that scientists judge evidence, and over time, they begin to come to agreement on it, and if they do come to agreement, we call that agreement consensus. And that consensus really then is what it is that we call scientific knowledge, the thing that scientific experts have agreed on. Now, this argument upsets a lot of people, it disturbs a lot of people because it appears to be a kind of appeal to authority. And in a way, it actually is. So this is, in a way, the controversial thing I want to say today, that actually, on some level, the belief in scientific evidence is an appeal to authority. But it's not the authority of an individual, which we've all been taught is a logical fallacy. It's the authority of a process by which scientific experts judge and evaluate evidence as a group. And if you look at this photograph here, if you ask yourself the question, well, what is this woman doing? What you see is that she is showing evidence, charts or graphs or illustrations or photographs, to a group of her peers. Now, I have to say I'm a little suspicious about whether these people are really scientists because they look much too happy. They also look way too diverse. But let's just accept for the sake of arguments that this is a wonderful group of happy, diverse scientists. Whoops, looks like I lost a slide here. Okay, so the point is it's not the authority of the individual, no matter how smart or brilliant it is, but the authority of the process You can think of it as a kind of group sourcing, or even a kind of wisdom of the crowd, even a kind of jury, but it's a special kind of jury or a special kind of crowd, a jury of scientific peers, a crowd of highly trained experts. Scientific knowledge, then, is the intellectual and social consensus of affiliated experts based on evaluating the weight of available evidence and evaluated according to diverse but nevertheless time-tested methodologies. So I want to conclude then with an analogy which I think many people find surprising, and it's an analogy to the modern car. Many of us have cars, many of us drive our cars on a regular basis, and we get in our cars and we turn on the engine in the morning to go to work or on the weekends to go away for the weekend. Our cars almost always start. Well, I actually had a 1964 Ford Anglia when I lived in Adelaide, and actually that car generally didn't start. But most cars nowadays do start, and they go where we want them to go. So how is it that the modern car is so reliable? It's not because of the genius of Daimler or Benz or Henry Ford. It's because the modern car is the result of the accumulated experience and expertise and work of thousands of automotive engineers who have worked on cars for more than a century. And that, I want to argue, is essentially the same as it is for science. Our scientific knowledge is reliable not because scientists use a particular kind of method, and not because individual scientists like Einstein and Darwin are geniuses, even though they are, but it's because science is, in effect, is actually the result of the accumulated experience, expertise, and observation of thousands and thousands and thousands of scientists who have worked on these problems over the course of centuries. So why believe in science? Because our scientific knowledge is based on the accumulated experience and expertise not of one genius, but of many people working together. And I should add, and the more diverse those people are, the more we should believe that the science is likely to be reliable. And conversely, if it's not diverse, that's a problem. So this is an important intellectual as well as moral argument for diversity. Science works like our cars because of accumulated expertise and experience. We should believe in science as a process because by and large that process has worked. But I want to leave you with one more thought, a thought that brings us back to Pascal and Pascal's wager. In the particular case of climate science, we should believe in science because if we don't, and we're wrong, then the consequences, as in Pascal's wager, are pretty darn dire. And conversely, if we do believe in climate change and later we find out it's a big hoax, well, then we created a better world for nothing. Thank you very much.